Yeah, hello. This is Abdul Latif from the Group R of the Group B class of Computer Science of the level 100. I am here to introduce the members of my group who are in the persons of Ibrahim Fauzia, who is here to talk about segmented memory. We have Frank Della, who is here to talk about page replacement strategy. We also have Joshua, who is here to talk about the page fault. Then we have Desmond Kakor, who is also here to talk about virtual memory. Please stay glued to your screen while we give you the insight and the in-depth integration of this entire topics of the operating system of the computer, which is very vital in the computer architecture.
My name is Desmond Ampoma, and for this presentation, I'll be tackling virtual memory. Now, one may ask what virtual memory is. Virtual memory is a memory management technique used by operating systems to give the illusion of a larger amount of available memory than physically exists. Virtual memory is a memory management technique employed by operating systems to expand the available memory space for running programs. So virtual memory is basically a technique that helps to increase the space that's used for running programs. So you can have let's say a RAM of 4 gig, but it might not be enough. So the computer uses this technique to increase or get more space for the computer to use in running programs. How does the virtual RAM work? It involves using a combination of physical RAM and disk space to store data. So with a virtual memory, it uses both the physical RAM and the hard disk to store data. So as the physical RAM is storing data, the hard disk is also storing some of the data. In virtual memory, each program is divided into smaller chunks called pages or segments. These pages are loaded into the computer's physical RAM as needed. However, not all pages of a program need to be loaded into RAM simultaneously. Instead, only the portions of a program that are currently being actively used or executed are loaded into the RAM, while the rest remain on disk. So basically, what this is saying is that the physical RAM, handles the programs which are currently in use, and the storage or the hard disk stores the program which are on suspense. When the physical RAM is fully utilized and the program requires more memory, and the program requires more memory, the operating system will select pages that are currently not in use and move them from the RAM to a designated area on the hard disk or solid state drive called a page file or subspace. This process is known as paging out. Action frees up space in the RAM to accommodate the new pages that the program needs. So when the RAM is full up, some of the page files which are on the RAM are being moved to the hard disk so that new programs which are being run or are being loaded will be able to load, since there will be space for them to load. If the program later accesses a page that has been moved to the page file, the operating system will page in that page by moving it from the disk back into the RAM. The dynamic swapping of pages between RAM and disk allows the system to utilize the larger storage capacity of the disk to simulate having more physical RAM available. So when a program or page file which is no longer being used is moved to the hard disk, and maybe the user wants to use what has been moved to the hard disk back, now a page file on the RAM which is currently not in use will come and swap the one which was then not in use but is now in use. And so the one which is now is which was previously on the hard disk will come back to the RAM. And this swapping of page files helps the PC to function better since there will be more room for the program to run. So without a virtual memory, let's say your PC offers you an address space of 4 gigabytes. 4 gigabytes. And an address space is an amount of memory allocated for a program or any device on the computer for them to store data inside. So let's say your program gives you 4 gig of address space. Now you want to load the program. The program loads the first address to the RAM. Let's say your RAM is 1 gig. So your program loads the first address to the RAM. Second address, third address. Now this is the fourth address. Now if you can see, there's no more space in the RAM for the program to load. With this, your program will crash since there's no more RAM to accommodate the address spaces in the physical RAM for the program to load. But with the virtual memory, it uses a mapping technique. So this is how the mapping technique works. If you have an address space of 4 gig, let's say the program loads this address, and this address will be mapped to any of the address spaces in the physical RAM. So 0 can be mapped to 1, 1 can be mapped to 0, 3 can be mapped to any. But here's the case: your physical RAM is 1 gig and here is 4 gig. So now you've used up all your 1 gig physical RAM. Now you want to load another address page file onto the RAM. So now this mapping technique will map the page file you want to load to the hard disk since there's no more space in the RAM. Mapping gives us the flexibility in how to reuse these RAMs, because in this one without the virtual memory there was no flexibility, it goes straight. But with this one, 0 can map to 2, 2 can map to 3, and the one which is being loaded and the one which is being loaded, the page file which is being loaded currently will be mapped to the hard disk since there is no more space left in the RAM. With the virtual memory, the program, let's say the program loads at the 0, it maps to let's take this second example. The program loads at the 0 and it is being mapped to the RAM. Loads address 1 is being mapped to the RAM. Loads address 2 is being mapped to the RAM. Loads address 3 is being mapped. Since program 1, 0 and 2 have made the RAM full, now there will be no space for program 3 to go on the physical RAM. So at this point, the virtual memory technique will take a will, will take a program which is so now let's take this example. We have a program which wants to run. The program loads address 0, address 1, address 2 and onto the address space. Now they all are being mapped onto the RAM. Now the RAM is full, but the program wants to load address 3. Since the program is full and we will not get anywhere to map it to, the virtual memory technique will get a program which is not currently in use. That means a program which is in suspense, and move it to the hard disk. That's what we call the page out, and we will now map the program, the address tray which the program is trying to load into the main memory, since that's the current address the program wants to load.
Hi everyone, my name is Fauzia Ibrahim, a group member of Group R, and I'm doing a presentation on segmented memory. Segmentation. Segmentation is a memory management scheme that supports user view of memory. A program is a collection of segments. A segment is a logical unit such as main program, procedures, logical variable, global variable, etc. Logical address space. Logical address space is also known as the linear address space. Address is D, where D is a number between 0 and 2k minus 1. When address uses k bits, segmented. Logical address space consists of a collection of segments where each segment is an independent linear address space. Address now consists of S, D, where S is the segment identifier and D is an address in the linear address space of the segment. Segmentation architecture. Logical address consists of two tuples, the segment number and offset. Segment table maps two-dimensional physical address. Each table entry has a base and a limit. The base contains the starting physical address where the segment resides in memory, whilst the limit specifies the length of the segment. Segment table base register points to the segment table's location in memory. Segment table length register indicates number of segments used by a program. Segment number is legal if segment is less than the segment table length. Since segments vary in length, memory allocation is a dynamic storage allocation problem. Segmentation hardware. A logical address consists of two parts, a segment number S and an offset into that segment D. The offset D of the logical address must be between 0 and the segment limit. When an offset is legal, it is added to the segment base to produce the address in the physical memory of the desired byte. Advantages and disadvantages of segmentation. Under the advantages, segments has defined length. It is possible to detect access outside of the segment. It throws new type of error, which is the segmentation fault or the addressing error. Disadvantages. How to place segment into main memory. Segments have different length. Programs are moved into memory and release memory. 2. Overhead to compute physical address from virtual address. This is the example of segmentation. The logical address is a collection of segments, while the segment table is made up of the limits and the base, and this is the physical memory. Let's move to paging. Paging is used to map a linear contiguous logical address space onto a linear physical address space. Physical memory consisted of fixed size blocks called frames. Size is power of 2 between 512 bytes and 60 megabytes. Logical memory consisting of blocks of same size called pages. To run a program of size n pages, need to find n free frames and load program. Paging sets up a page table to translate logical to physical addresses. Address translation scheme. Address generated by CPU is divided into page number and page offset. Page number is used as an index into a page table which contains base address of each page in physical memory. Page offset is combined with base address to define the physical memory address that is sent to the memory unit. For given logical address space 2M and page size 2N. Let's move on to implementation of page table. Page table is kept in main memory. Page table base register points to the page table, whilst page table length register indicates size of the page table. In this scheme, every data or instruction access requires two memory accesses, one for the page table and one for the data or instruction. The two memory access problem can be helped by the use of a special fast lookup hardware cache called associative hardware or translation look-aside buffers. Paging hardware with TLB. Some TLB stores address space identifier in each TLB entry. Address space identifier uniquely identify each process to provide address space protection for that process. Otherwise, need to flash at every context switch. On a TLB miss, a value is loaded into the TLB for faster access next time. Some entries can be wired down for permanent fast access. Now, memory protection. Memory protection implemented by associating protection bits with each frame to indicate if read-only or read-write access is allowed. Memory protection can also add more bits to indicate page execute only and so on. Valid invalid bits attached to each entry in the page table. Valid. Valid indicates that the associated page is in the process, the logical address space, and is a legal page. The invalid indicates that the page is not in the process, which is the logical address space. Or you can use page table length for it. Any violation results in a trap to the kernel. Here on shared pages, and under it we have shared code and private code and data. Under the shared code, we have one copy of read-only code shared among processes, which is the text editor, compilers, or window systems. 2. Similar to multiple threads sharing the same process space. 3. Also useful for inter-process communication if sharing of read-write pages is allowed. Private code and data, and under it we have each process keeps a separate copy of the code and data. 2. The page for the private code and data can appear anywhere in the logical address space. And that is the end of my presentation on segmented memory. Thank you for watching.
My name is Joshua Dyer and this is my submission on page faults. So what are page faults? A page fault is a type of exception raised by computer hardware when a running program accesses a memory page that is mapped into the virtual address space but not loaded into physical memory. A page fault occurs when a program tries to access a portion of its virtual address space that is not currently in physical memory, or as we call it, the RAM. In simpler terms, it's like a program requesting a page that isn't currently loaded in the main memory. So what are the causes of page faults? Number 1, demand paging. Operating systems often use a technique called demand paging, where only the pages that are actively needed are loaded in physical memory. Other pages remain on the disk until they are required. This helps conserve memory space. So the reason this is a cause of page fault is that with demand paging, it only loads a page when it is requested by the program. So in the case where a program requests a page that hasn't yet been loaded into the memory, it causes a page fault. Number 2, initial program load. When a program is first loaded into memory, not all of its pages are immediately loaded. Only the essential pages. An example is the program code that is loaded initially. Other pages are loaded as needed during program execution. Number 3, page swapping. If physical memory becomes full, the operating system might need to swap out some pages to disks temporarily to make space for new pages. When the swap out page is needed again, a page fault occurs, triggering the page to be swapped back into memory. Lastly, copy on write. In certain cases, when a process creates a new child process, the child process shares memory pages with the parent process until either process modifies the page. When a modification occurs, the page is copied and a page fault happens. Handling page faults. When page fault occurs, the operating system takes some steps to ensure that program execution is not interrupted. And the following are the steps taken by the operating system to handle page faults. Number 1. The first step, page fault trap. The processor raises a hardware interrupt called a page fault exception when a page fault occurs. This transfers control to the operating system's memory management routines. Secondly, it determines the faulting page. The operating system determines which virtual page the program was trying to access and whether that page is currently in the physical memory or not. The third step, the operating system fetches the page. If the page is not in memory, also known as a page miss, the OS initiates a process to fetch the required page from disk into an available page frame in physical memory. This could involve swapping out another page if memory is full. And lastly, it updates the page tables. The operating system updates the page tables to reflect the new mapping of the virtual page to the physical page frame. The following are the impacts of page faults. Number 1, performance degradation. Page faults can lead to performance degradation because they involve the time-consuming process of moving data between RAM, that is the primary memory, and secondary storage. Examples are the hard drive or SSD. When a page fault occurs, the CPU must wait for the necessary data to be loaded into RAM before it can continue executing the program. This can result in noticeable delays and reduce system responsiveness, especially if page faults occur frequently. Number 2, increased input and output operations. Page faults typically involve reading or writing data to and from secondary storage devices. These input and output operations can place a significant load on storage subsystems and can lead to increased wear and tear on storage media, potentially impacting their longevity. Excessive page faults can also saturate input and output channels, causing bottlenecks that slow down other disk-intensive tasks. And lastly, it increases wear and tear on storage devices. Frequent page faults, especially when they result in a significant amount of data swapping between RAM and storage and secondary storage, can lead to increased wear and tear on storage devices like drives and SSDs. The constant reading and writing of data to storage can reduce the lifespan of these devices over time. So in conclusion, page faults are a fundamental aspect of virtual memory management. They enable efficient memory usage by allowing programs to work with more memory than is physically available. Understanding the causes, handling process, and impact of page faults is crucial for building and maintaining high-performance computer systems. Thank you.
Hello, this is Frank, and I'm doing a presentation on page replacement strategies. So when we see page replacement strategies, page replacement strategies or algorithms are techniques used by the computer system to decide which memory pages to swap out, write to disk, or remove from main memory when a page of memory needs to be allocated. They play a crucial role in virtual memory system where the main memory, RAM, acts as a cache for the secondary storage, typically hard drive or SSD. The main objective of these strategies is to reduce the page fault rate, which occurs when a requested page is not found in the main memory, necessitating a slower retrieval from the secondary storage. Different strategies have been devised to optimize memory access patterns and to strike a balance between system overhead and performance. To move on, we have to talk about the difference between virtual memory and page replacement strategies. Virtual memory, the definition for it is a memory management capability that allows an OS to use a mix of physical memory and disk storage to give the illusion of more available memory than is physically restored. For the page replacement strategies, this is algorithms or techniques employed by the OS to decide which memory pages to evict when a new page needs to be loaded onto full memory. For the purpose, virtual memory allows execution of larger applications simultaneously than would fit in physical memory. Page replacement strategies, well, it says optimize performance by reducing the number of page faults. For the examples, virtual memory is paging and segmentation. For page replacement strategies, there is FIFO, LRU, optimal page replacement, etc. The implementations for virtual memory, it uses both hardware, which is the memory management unit, and software, which is part of the OS, to manage mapping between virtual and physical addresses. For page replacement strategies, components of a virtual memory system becomes crucial when deciding which page to keep in physical memory and which to remove to disk. For the relations, when it comes to virtual memory, the overarching system providing extended memory space using RAM and disk storage. For page replacement strategies, it is specific algorithms used within a virtual memory system to manage contents. So, we move on to the common page replacement strategies. Number one, which is the FIFO, first in, first out. This is the simplest page replacement algorithm. In this algorithm, the operating system keeps track of all pages in the memory. In a queue, the oldest page is in the front of the queue. When a page needs to be replaced, page in front of the queue is selected for removal. Here is a summary of everything I said. A. The oldest page in memory is the first one to be replaced. The B. Implements using a queue. The oldest page is at the front. C. Simple but may not always provide the best performance. So we move on to how does the FIFO page replacement work. FIFO is implemented in the operating system by keeping track of all pages in the queue. The newest page is at the head of the queue and the oldest is at the first page is in the tail. 1. The OS maintains a list of all pages which are residing in the memory. 2. When a new page prints from the secondary memory. 3. The new page requests the main memory. 4. On a page fault, the head of the list, example, the oldest, will be removed. 5. The new page will be added at the tail of the list. So the oldest is always at the front and the new is always at the back. That's all that it says. Now let's go to how FIFO page replacement work. Now before that, the page fault has already been said, but I would like to go over it again. It says page fault occurs when a page requested by a program running in the CPU is not present in the main memory, but in the address page of the program. A page fault generally creates an alert for the OS. Now here's a flowchart explaining everything I said. So from the start, send page request. The page sends page request. Now it goes to page found. Whether it's found or not, if it's found, it goes to hit and then it stops. But if not found, it goes to fault. Then it now goes to fetch page. It searches the page and now it goes to stop. There's a simple explanation. Now let's move on to the second page replacement strategies. Optimal page replacement. In this algorithm, pages are replaced which would not be used for the longest duration of time in the future, which is somehow a temporary page replacement way. Now, A replaces the page that will not be used for the longest period of time in the future. B consider the best strategy in terms of the number of page faults. C. Difficult to implement in practice since it requires feature knowledge of the access secret. As we move on, we go to the third one. It says LRU, least recently used. LRU is widely used and effective cache replacement strategy that bases its decision on the recency of item access. However, as with all caching strategies, its effectiveness. A. Replaces the page that hasn't been for the longest period of time. B. Can be implemented using counters, stacks, or doubly linked lists. C. Tries to approximate the optimal strategy by using recent history as a prediction for future requests. Thank you. This is the end of my presentation.
After watching our video, I hope myself as well as my team has been able to give you all you need to know about segmentation, page replacement strategies, page fault, as well as virtual memory. Please hit the like button if you really enjoyed our video, and we hope to give you more information about things or everything that has to do with computer architecture as well as other. Thank you.